Welcome to this lecture on the nature of econometrics and economic data. Here's what we'll cover today. We'll start by defining econometrics itself, what it actually is, and what makes it different from plain statistics. Next, we'll walk through the steps involved in empirical economic analysis, the actual workflow researchers follow, from an economic question all the way through to a tested model. We'll then look at the different types of economic data you'll encounter, cross-sectional, time series, and panel data, and why the type of data shapes the methods you can use. After that, we'll tackle one of the hardest problems in economics, establishing causality. We'll talk about the idea of ceteris paribus and what counterfactual reasoning really means. Let's set out what you should be able to do by the end of this lecture. First, you should be able to explain the scope and purpose of econometrics in economics and business. Second, you should be able to apply the 4 steps of empirical economic analysis to a real research question of your own. Third, you should be able to take an economic model and turn it into an econometric model, interpreting every component, the variables, the parameters, and the error term. Fourth, you should be able to identify and tell apart cross-sectional data, time series data, and panel data. Fifth, you should understand the random sampling assumption, and just as importantly, recognize the situations where it breaks down. Sixth, you should be able to distinguish experimental data from non-experimental or observational data. Seventh, you should be able to define ceteris paribus and apply it when thinking through policy and economic questions. Eighth, you should be able to explain counterfactual reasoning and what's known as the fundamental problem of causal inference. Ninth, you should be able to spot omitted variable bias, reverse causality, and selection bias when they show up in applied work. Finally, you should be able to apply all of this by solving empirical exercises involving data types, causality, and research design. Let's get started. Let's begin with the most basic question. What is econometrics? We'll look at its scope, its formal definition, and the toolkit it brings together. Here is the formal definition. Econometrics is the application of statistical and mathematical methods to economic and business data, and it serves 3 purposes: to give empirical content to economic relationships, to test economic theories, and to evaluate policy. You can think of econometrics as sitting at the intersection of 3 fields: economics, mathematics, and statistical methods. Take any one of them away, and you don't really have econometrics anymore. Its real job is to bridge the gap between qualitative economic theory, ideas like demand falling as price rises, and quantitative real-world data that lets us actually measure how much. Economics contributes the theory. It tells us which relationships matter and gives us the questions worth testing in the first place. Mathematics takes those qualitative ideas and formalizes them into precise equations we can actually work with. And statistics applies the methods for estimating those equations from data and testing whether our hypotheses hold up. So why is econometrics treated as its own field rather than just applied statistics? Part of the answer is that econometrics serves 3 core uses in practice. The first use is testing economic theories. For example, does raising the minimum wage actually reduce employment, as basic theory predicts? The second is empirical policy analysis, putting an actual number on the causal effect of a policy intervention, not just saying it has some effect. The third is forecasting, using past patterns in the data to predict things like GDP growth, inflation, or exchange rate. So what actually separates econometrics from pure statistics? There are 2 key differences. First, economic theory guides the model itself. It tells us which variables belong in the model, what sign we expect each coefficient to have, and which way causation should run. Second, econometrics relies primarily on observational, non-experimental data. We can't run a controlled experiment on the entire economy to see what happens to wages or GDP. We have to work with the data the world happens to give us. Let's ground this in real applications. In policy, In academic research, econometrics is used to ask questions like, does education actually cause higher wages? Does job training genuinely improve worker productivity? Or do we just see a correlation? Does raising the minimum wage reduce employment? Does putting more police on the street actually reduce crime? Does applying more fertilizer increase crop yield? A question we'll come back to as a worked example later. Does having electricity at home reduce fertility rates in developing countries? Does alcohol abuse cause unemployment, or could the relationship run the other way? Are mortgage applications approved at equal rates across racial groups, holding everything else constant? Does a smaller class size improve students' test scores? Does a state's corporate tax rate affect its economic growth? These are exactly the kinds of questions econometrics is built to answer. Econometrics is just as central in business and finance. It's used to forecast GDP, inflation, and interest rate. It's used to test asset pricing models like the CAPM and arbitrage pricing theory. It's used to test the expectations hypothesis in bond markets. It's used for credit risk modeling and predicting loan defaults. It's used for demand estimation and measuring price elasticity. It's used to evaluate advertising effectiveness and the broader marketing mix. It's used to estimate the returns to schooling and how wages are determined. It underlies earnings and schooling regressions, which we'll actually work through ourselves shortly. It's used to build factor models for portfolio management. And it's used to evaluate trading strategies and test market efficiency. As you can see, this toolkit shows up everywhere economic and financial decisions are made. Now that we know what econometrics is, let's look at how it's actually done. The steps that take us from theory to a model to data, and finally to inference. The first step is always to state your economic question precisely. For example, what is the causal effect of job training on hourly wages? Notice how specific that is. You need to be explicit about exactly which population you're studying and the direction of the relationship you're interested in. You also need to clearly state who the study is actually about. For instance, low-income men in the United States rather than workers in general. The second step is to specify an economic or conceptual model. Here you draw on economic theory. Human capital theory, for example, tells us that wages should depend on education, experience, and ability. Theory does double duty here. It tells you which variables to include, and it tells you the sign you should expect on each relationship before you've even looked at the data. Conceptual models let you specify these relationships mathematically before you start worrying about what data is actually available to you. The third step is to translate that conceptual model into an econometric model. This means choosing a functional form, say a log linear specification, and adding an error term, U, to capture everything we can't observe or measure. Here's what that looks like in practice. The log of wage equals beta 0 plus beta 1 times education, plus beta 2 times experience, plus beta 3 times training, plus the error term U. That error term U is doing a lot of work. It's silently collecting every wage determinant we cannot observe or measure, like innate ability or motivation. The fourth and final step is to collect data, and then estimate the model, test hypotheses about it, and use it to forecast. In practice, this usually means using OLS or another estimator to obtain estimates of each beta coefficient. From there, you construct confidence intervals and test hypotheses. For instance, testing whether beta 1 equals 0, which would mean education has no effect at all. Finally, you interpret the results in economic terms and check how well the model fits using R-squared and related statistics. Mastering this four-step cycle, question, model, econometric specification, estimation, is really the backbone of all empirical econometric work. Let's see this whole process side by side using the classic wage equation. On the left, the economic model from human capital theory simply says wage is a function of education, experience, and tenure. Theory tells us the direction, but not the exact magnitude. To turn this into an econometric model, we add a functional form assumption and a random error term. The result: log of wage as the dependent variable. Using the log lets us interpret the slope coefficients as percentage changes. Education, experience, and tenure become our explanatory variables. The regressors. Beta 0 through beta 3 are the unknown population parameters we want to estimate. Beta 1, for instance, is roughly the percentage wage gain from one more year of education. And U is the error term, soaking up everything we can observe: ability, motivation, family connections, plain luck. Let's make this concrete with a real example. Using data from the National Longitudinal Survey of Youth, 500 respondents and their 2011 earnings, we get this estimated regression. Earnings equals 0.76 plus 1.2, 7 times years of schooling. With a sample size of 500, let's interpret what these numbers actually mean. Let's break down each piece of this regression economically. Slope 1.27 tells us that each additional year of schooling is associated with a $1.27 increase in predicted hourly earnings. The intercept, 76 cents, is the predicted hourly wage for someone with 0 years of education. Economically, that's really just an extrapolation. Almost nobody in the sample has 0 schooling, so this number has little practical meaning on its own. R squared of 0.086 tells us that years of schooling alone explain only about 8.6% of the variation in hourly earnings. That leaves over 91% of the variation explained by other things entirely: experience, ability, motivation, luck, family wealth. And here's the critical warning: this is just a raw correlation. It does not by itself establish that schooling causes higher earnings. Let's shift gears and talk about the different types of economic data you'll work with: cross-sectional, time series, and panel data. Understanding the structure of your data matters because it dictates which econometric techniques are even valid. Cross-sectional data means observing many different units, people, firms, countries, at one single point in time. The order of these observations doesn't matter, and the key assumption underlying this type of data is random sampling. This will be our primary focus going forward. Time series data is the opposite. It's one unit, say one country or one company, observed across many time periods. Here, ordering is critical because today's value can depend on yesterday's. This creates a typical complication called serial correlation, which we'll introduce in more detail later. Panel data combines both, many units observed across many time periods. It lets you control for unobserved traits that don't change over time, which is extremely powerful. For this course, though, our main focus will be on cross-sectional data. Let's look more closely at cross-sectional data, starting with its formal definition. Cross-sectional dataset is a sample of individuals, households, firms, cities, states, or countries, all collected at essentially the same point in time. Crucially, the order in which these observations appear in your dataset doesn't matter at all. You could shuffle every row and you wouldn't lose any information. This kind of data rests on a key assumption: random sampling. Random sampling means each observation is an independent draw from the same underlying population, what statisticians call IID, independent and identically distributed. And this assumption holds. The statistics we calculate from our sample reliably estimate the true characteristics of the population. Random sampling really is the bedrock that the rest of cross-sectional econometric theory is built on. Here's what a typical cross-sectional dataset looks like in practice: a wage survey, where each row, I, is one individual, and the order of those rows carries no meaning whatsoever. But random sampling can be violated in several ways. When the sample is self-selected, such as volunteers. When non-response is systematic. For example, high earners refusing to report their wages, or when the data is clustered geographically. You'll see this kind of cross-sectional structure constantly in wage surveys, school test data, loan applications, birth weight studies, and crime data by county. Now, let's turn to time series data and look at how it's defined. A time series dataset consists of observations on one or more variables, tracked over time for a single economic unit. Here, ordering is absolutely essential. Past values can genuinely cause or influence current ones. If you shuffle a time series, you would destroy the very structure that makes it useful. Let's look at some concrete examples of time series data. On the macroeconomic side, think of the annual U.S. minimum wage from 1950 to 2023, quarterly UK GDP, or the monthly consumer price index measuring inflation. On the financial side, think of daily stock prices, or 3-month and 6-month Treasury bill interest rate. In every one of these cases, each row in the dataset represents a distinct time period, which we usually label T. Time series data brings its own special set of challenges that cross-sectional data doesn't have. First is serial correlation, or autocorrelation. Observations are typically not independent across time. Unemployment today is strongly related to unemployment yesterday, for example. The second is spurious regression, caused by shared trends. Two variables can drift upward together over time simply because of some third underlying factor, making it look like they're related when they aren't. The classic example being that the number of TV sets and falling infant mortality both trended upward for decades, with no causal link between them. Third is seasonality. Ice cream sales and swimming pool usage both rise every summer, but that's a shared seasonal driver, not one causing the other. And the fourth is that policy itself is rarely set randomly. Governments change the minimum wage, for instance, in response to economic conditions, not at random. Standard always assumes independent observations, and in time series, that assumption is routinely violated. Here is the side-by-side comparison of all three data structures. As a reminder, our focus in this course will be primarily on cross-sectional data. Now we get to what is arguably the central challenge in all of empirical economics: causality, the idea of ceteris paribus, and counterfactual reasoning. Distinguishing correlation from causation is really what motivates almost every advanced technique in econometrics. The central challenge in empirical economics is this: just because we observe a statistical association between X and Y does not mean X causes Y. Finding a correlation in the data might be suggestive, but it's rarely conclusive on its own. Let's look at some classic spurious correlations to see why. Ice cream sales rise and drowning deaths rise together, but both are driven by hot weather, not by each other. Countries with more televisions tend to have lower infant mortality, but wealth drives both of those things. The TVs themselves aren't saving babies. Cities with more police officers tend to have more crime. But that's reverse causality. High-crime cities are the ones that hire more police in the first place. So why exactly does correlation fail to establish causality? There are three distinct reasons. First is confounding or omitted variables. This happens when some third variable z causes both x and y, creating a statistical association between them, even though x has no direct causal effect on y at all. The second reason is reverse causality, also called simultaneity. This is when y actually causes x, or x and y cause each other simultaneously. Police presence and crime rates, for instance, are determined together in equilibrium, not in one fixed direction. The third reason is selection bias. This happens when individuals self-select into the treatment group based on unobserved characteristics that also affect the outcome. For example, highly motivated workers being the ones who choose to sign up for training. Any one of these three problems is enough to bias a simple Ohl's correlation. Let's define the causal effect itself precisely. The question we're really asking is, how does variable y change if we change variable x, but hold absolutely everything else constant? Normally, the causal effect of x on y is the change in y caused solely by a one-unit change in x, with everything else held fixed. This is the central quantity that most empirical economic research is actually trying to estimate. Take education and wages as an example. Does an extra year of education actually cause wages to rise? Or is it that naturally more able people both choose more schooling and happen to earn more, with ability being the true driver behind both? To find the true causal effect of education, we need to isolate it by holding ability and other traits fixed. This brings us to one of the most important phrases in economics, ceteris paribus. It's Latin for other things equal, and economic relationships are almost always implicitly stated this way. For example, when we say demand falls as price rises, what we really mean is holding income, consumer tastes, and all other prices constant. So how do we actually achieve ceteris paribus inside an econometric model? In multiple regression, including observable confounding variables as controls, is our statistical way of holding other things fixed. If a confounder, like innate ability, can't be observed, we simply can't control for it directly, and that leads to omitted variable bias. Isolating that true ceteris paribus effect from observational data is really the primary challenge of econometrics. Let's see ceteris paribus achieved perfectly through a controlled, randomized experiment. The research question, does applying more fertilizer increase soybean crop yield, all else equal? Here's how you'd run the experiment. Divide a large agricultural field into many equal-sized plots, and randomly assign a different amount of fertilizer to each plot, and measure the crop yield on each plot at harvest. Why does this work? Because randomization ensures that the fertilizer level each plot gets is completely independent of every other factor: rainfall, sunlight, land quality, soil type, pest exposure, all of it. Randomization balances out all confounders, both the ones you can observe and the ones you can't, evenly across every treatment level, which means any difference in average yields you observe between plots can confidently be called causal. This is a randomized controlled trial, or RCT, and it's the gold standard for causal inference. Now let's see what happens when that randomization breaks down. Suppose the research assistant isn't randomizing at all. She puts more fertilizer on the plots that already have better land, hoping to maximize yield. Here, better land quality is a confounder. It directly increases crop yields on its own. And now, better land quality is also correlated with getting more fertilizer, which means the relationship between fertilizer and yield is now spurious. If you ran an Ohl's regression on this data, your estimate of fertilizer's effect would overstate the true causal effect. And here's the key parallel. This non-random allocation of fertilizer is exactly the same problem as self-selection in human data, like workers choosing their own level of education. Let's now look at education and wages directly, where this exact same selection problem shows up. Research question: what is the causal effect of an additional year of education on hourly wages? Why is this so hard to answer using observational data? Because people choose their own level of education. They are not randomly assigned to stay in school or drop out. Individuals who get more education differ systematically in many ways from those who get less. There are two key unobserved confounders at play here. The first is innate ability. More able people tend to both get more education and earn more. Ability is driving both outcomes. The second is family background. Wealthier families tend to provide better schooling and better job networks. Because of these two confounders, a simple correlation between education and wages will overstate the true causal effect. This is omitted variable bias, the single most common form of what economists call endogeneity, and it maps perfectly onto our fertilizer example. Rainfall corresponds to experience. It's observable, so we can measure it and control for it directly in a regression. Land quality corresponds to innate ability. It's inherently unobservable, or at least very hard to measure, just like soil quality is hard to fully capture in a few variables. And the consequence is the same too. If high-ability people, like better land, choose more education, like more fertilizer, then OLS will attribute the effect of ability to education instead, biasing the estimate upward. Let's look at one more example. Police and crime, a question of real public policy interest. Does having more police officers on the street deter crime? Here's the ceteris paribus thought experiment. If a city were randomly given 10 additional police officers, by how much would its crime rate fall? Equivalently, imagine two cities that are identical in every respect except one has 10 more officers than the other. What's the difference in crime between them? To answer that, we need to isolate the effect of policing by holding every other characteristic of the city fixed. Cities don't randomly assign their police force size. It's a policy decision that's directly correlated with the crime rate itself. This introduces a different form of endogeneity, simultaneity bias. Cities with high crime rates tend to hire more police. So the causal arrow can run in both directions at once. This means a naive OLS regression might actually show a positive correlation between police and crime, making it look absurdly as if more police cause more crime. In reality, crime levels and police staffing are simultaneously determined together in equilibrium. Neither one is purely the cause of the other. This brings us to a broader issue: why simple group comparisons fail to identify a causal effect. The average wage of graduates minus the average wage of non-graduates is not the same thing as the causal effect of education. We can actually decompose that observed gap into two distinct pieces. The observed difference equals the true causal effect, plus a selection bias term. Normally, the selection bias is the expected difference in the untreated outcome between those who choose treatment and those who don't. In plain terms, it's the gap in what the two groups would have earned anyway, even without the extra education, simply because of who they are. High-ability people are the ones who tend to get more education. That selection bias is positive, and OLS ends up biased upward. This is exactly why correlation does not equal causation. To solve this, we need causal strategies that isolate variation that's truly exogenous, unrelated to these confounders. Take a job training example. Firm A offers training and firm B doesn't. Higher output at firm A might just reflect better workers, or better technology at firm A, not the training itself. Capital stock, technology, manager quality, and worker ability can all affect output independently of whether training was given. So a simple comparison of firm A versus firm B is biased by all of these confounding factors. We see exactly the same pattern with police and crime. Cities with high crime hire more police, so a simple correlation shows more police associated with more crime. But that positive correlation just reflects how policy gets selected. It tells us nothing about whether police actually deter crime. So what strategies actually let us establish causality? The first is the randomized controlled trial, randomly assigned treatment versus control. Random assignment breaks the link to confounders entirely. It's the gold standard, though it's often rare, expensive, or simply infeasible in economic settings. The second strategy is multiple regression with controls. Include every observable confounder as an additional regressor. If you genuinely capture all the relevant confounders, OLS will consistently estimate the causal effect. This is the core estimation method we'll build on throughout the course. The third strategy is instrumental variables, or two-stage least squares. Find a variable z that affects the treatment, but affects the outcome only through that treatment. This isolates exogenous variation and removes selection bias from unobservables. We'll cover this in detail later in the course. And the fourth strategy is natural experiments and regression discontinuity designs, exploiting sharp cutoffs like test score thresholds, geographic borders, or specific dates that create variation in treatment that's essentially as good as random, without an actual experiment. Let's close with a complete glossary of the key terms from this lecture. Econometric model. a quantitative estimable equation that translates economic theory into a testable form, including an error term. Economic model, a qualitative, theoretical description of the relationship between economic variables before it's been formalized into an estimable equation. Empirical analysis, the use of statistical methods on real data to test theories, estimate relationships, and produce forecasts. Cross-sectional data, a sample of many units observed at one point in time, where ordering doesn't matter, and the key underlying assumption is random sampling. Random sampling, each observation is an independent draw from the same underlying population distribution. Time series data, one unit observed across many time periods, where ordering matters and serial correlation is a typical complication. Panel data, many units observed across many time periods, combining both dimensions, though it's not the main focus of this particular course. Experimental data, data where treatment is randomly assigned, allowing for clean causal inference. This is the gold standard. Non-experimental data, data where units self-select into treatment. This describes most economic data, and it's subject to confounding and selection bias. Causal effect, the change in y caused solely by a change in x, with all other factors held constant. Ceteris paribus, Latin for other things equal, the defining principle behind every causal economic relationship. Counterfactual outcome, the potential outcome under the alternative treatment state, something that is fundamentally unobservable in the real world. Counterfactual reasoning, comparing actual and hypothetical outcomes in order to infer causality. Selection bias, bias arising from non-random treatment assignment that's correlated with the determinants of the outcome. Omitted variable bias, bias from excluding a relevant variable that's correlated with the regressors you did include. Let's recap everything we've covered today against our original learning outcomes. First, we defined econometrics and articulated its three core purposes. Second, we covered how to apply the 4 steps of empirical economic analysis to any research question. Third, we learned to construct and interpret an econometric model derived from economic theory. Fourth, we learned to identify and distinguish cross-sectional data, time series data, and panel data. Fifth, we explained the random sampling assumption and when it breaks down. Sixth, we distinguished experimental from non-experimental data and discussed the implications of that distinction. Seventh, we defined ceteris paribus and applied it to policy and empirical economic questions. Eighth, we explained counterfactual reasoning and the fundamental problem of causal inference. Ninth, we learned to identify omitted variable bias, reverse causality, and selection bias in real, applied settings. And 10th, we put it all into practice, solving applied empirical exercises on data types, causality, and research design. So here's the key takeaway from today. Econometrics gives us rigorous tools to estimate causal effects from real-world data, but only when we genuinely understand our data, recognize its limitations, and choose methods that are appropriate to the causal question we're actually trying to answer. In our next topic, we'll move on to the simple regression model. Thank you for tuning in to Topical Brew. Keep practicing, stay curious, and make sure you're subscribed with notifications turned on so you're ready for our next topic. If a concept felt a bit tricky today, or if there's a specific challenge you want me to break down in the next video, let me know in the comments.